In this video for section 6.4 of the text, we're going to learn how to find the length along a curve, which is different than finding the length of a straight line distance. So let's start with what we know about the distance formula of a straight line distance. So we know that the distance between the 2 points P1 and P2 is the square root of the sum of the squares of their differences, as this. So it's the square root of the sum of the squares of the difference of their y coordinates and the square of the difference in their x coordinates. So let's see that pictured. What we're actually doing is finding the hypotenuse of this triangle, and the difference in the x coordinates is this leg of the right triangle, and the difference in the y coordinates is that leg of the right triangle. So if this leg of the triangle is labeled A, this is labeled B, this is labeled C, then we're just using the Pythagorean theorem to say that C is A squared plus B squared. Take the square root of that. So we're going to extend this distance formula to see how it can be used to find the lengths of curves. So let's do that on the next blackboard. So what we are trying to find is this length of curve that is marked in blue. Length of the curve between this point, which is A comma f of A, and between this point right here, which is B comma f of B. So we're trying to find this length along the curve. And we're going to approximate this length along the curve by this length of the hypotenuse of a triangle. So we're going to assume that we can use the distance formula. So this hypotenuse that is in red in the drawing will be our C, this side of the triangle will be our A, and this side of the triangle will be our B, and that gives us that this C, let's also call it L for length. L will be the square root of the difference in the y values, which is f of b minus f of a squared, plus the difference in the x values, which is b minus a squared. So we're using the Pythagorean theorem. So, however, what we really want to find is not this red hypotenuse, but this blue length along the curve. And so this is going to, if we call that blue length along the curve script L, that is going to be this regular L here is going to be an approximation for what we want to find. So how do we make that approximation better? Well, we make the distance between A and B smaller. So let's see how that looks if we just make the distance between A and B half what it is in this case. So you can see that in our first case there was quite a bit of difference between the red approximation and the blue actual, whereas here the difference between the red approximation and the blue actual is much smaller. And so if we use calculus to help us out here, we can divide this length of arc that we want to find up into a large number of pieces, x on the x-axis between x0 and xn, where x0 is A, xn is B, and then this is x1, x2, and what we have represented in the general case here is xi minus 1 and xi, and we're just adding up the length of the arc on this n pieces of arc. But if the difference between these x values is very close together, our error is going to get less and less and less. So on the next blackboard, let's see what happens when the difference between xi and xi minus 1 goes to 0. Now back on this setup slide, I should have subtracted the two f of x values. I had that written incorrectly before. So as we say what we're doing, now we're taking the limit as the delta xi goes to 0. And to make it so, this is just what we had on the previous slide. To make it so that we can actually take this limit, we're going to divide this by delta x sub I squared, and we're going to divide this by delta x sub I squared, and then we're going to multiply, since we're dividing by delta x sub I squared under the square root, we have to then outside the square root multiply by delta x sub I. So what we're going to do is we're going to look at these two terms under the radical, this term and this term. Well, this term is the easy one to look at. Xi minus 1 is just delta xi, so this term right here is just 1. This term right here we're going to take out and look at it. So what we really have is, if we write it just a little differently, f of xi minus f of xi minus 1 divided by delta xi is the same as xi minus 1, and the numerator and the denominator are squared. But let's put the square here on the outside of this, and let's say we're taking the limit as xi goes, or xi minus 1 goes to xi. And that should look familiar. It should look like a derivative formula we learned in Calculus 1. It should look like this, right? The limit as as x goes to a of f of x minus f of a over x minus a. In Calculus 1 we called that f prime of a, right? So if we use that here, then this expression underneath the bracket squared should go to f prime, not of a in this case, but remember when this x value went to this x value, we got the derivative at this x value. So it's not f prime of a, it's f prime of x sub I. So if we go to our next blackboard, just write in what we found. That went to f prime of xi, but we're summing up all of those, so instead of it being xi, it's just f prime of x squared. Well, actually, let's do it in two steps. So it's the summation I equals 1 to n. So it's the limit as delta xi goes to 0, summation I equals 1 to n, f of xi squared plus, and remember the other term here, right here was 1, and so this is plus 1. And what happens when delta x's go to 0, summations turn into integrals? Whoops, I forgot. Remember that this thing was multiplied on the outside by delta xi, so there is a delta xi here, and as delta xi goes to 0, that becomes a dx, the summation sign becomes an integral, and the subscript I disappears, and we just get f prime of x squared plus 1, and that is our arc length formula. So it's really just a variant of the Pythagorean theorem. You can kind of see here that this is the a squared here, and this is the b squared here, and we're just getting all the c squareds with the error going to 0. So let's do a couple of examples. Do the same ones that are in the book. So we're going to do first example 1 on page 126. So we're trying to find the length along the curve between 0, 0 and 1, 1. That's the length in blue. And if we use the approach that we had in the book, we know that we're going to approximate it by using smaller and smaller hypotenuse estimations. Let's calculate the first hypotenuse, right, the largest one possible. We haven't broken it down. That distance between the points 0, 0 and 1, 1 is going to be the square root of what? 1 minus 0 squared plus 1 minus 0 squared. And so that's the square root of 2, which is approximately 1.414. And so we should get some distance a little bit longer than that. So let's see what we get when we set this up. So the formula, the arc length formula, requires that we know the derivative of the function and that we square that. So the derivative of f of x is 2x, and we're going to square that. So the arc length is the integral between 0 and 1 of the square root of f prime of x, which is 2x squared plus 1, and that is this. The integral 0 to 1 square root of 4x squared plus 1 dx. Well, this is an integral that we can't do, and it turns out that in practice a lot of times when you're working with even relatively simple functions, you have integrals that you are not able to do. You should be able to get this answer on your graphing calculator. We'll look at alternate software that will give us answers to these kinds of problems. But what we get is an answer of approximately 1.479, and that was compared to the straight line distance, which was 1.414. So it is about, what, 0.065 more than, oops, this distance here of the actual arc is about 0.065 more than the very gross estimate we would get by just finding the straight line distance. Just notice that if we had, if we would continue this, or continue the curve so that it's not just 0 to 1, but 0 to 2, we're trying to find the length of this blue length versus just trying to find the whole thing as a straight line distance, and you can see that the error starts to get larger. It was 0.065 last time, and if we go a little bit further now, the error is about, what, 0.42. So the straight line distance approximation is not going to be very good for very long, and so if we need the kind of accuracy you need in application problems, you definitely are going to need to find the arc length using the arc length formula. Let's do one more example of this type where the functions are a little bit different, and that's going to be example 2 on page 126. So we have a special function here whose derivative is going to actually allow us to resolve the square root of f prime of x squared plus 1. So f prime of x, so we take its derivative, gives us, what, x cubed, and we take the derivative of this term, bring the minus 2 down, we get minus x to the minus 3 over 4. And when we square f prime of x, let's see what we get. So let's square that using a big blackboard to do it, because it's a little bit more complex, the algebra, than you might guess. So remember, we're foiling it, so let's write it so that it's easier to see what the FOIL is. So instead of writing it squared, let's write as term times term. And then we can do first, inner, outer, last. So first is x cubed times x cubed. And this product would be I. This product here would be O. And then this product here would be L. Okay, so F is x cubed times x cubed, which is x to the 6. And here's where it gets interesting, or the reason we chose this problem. The inner is x to the minus 3 over 4 times x cubed, and the outer is x cubed times x to the minus 3 over 4. So you can see that both the inner and the outer, because when we add the exponents we get 0, so the inner is 1/4 and the outer is 1/4, and then the last is x to the minus 6 over 16. So if we summarize that, we've got this, that when we square the derivative we get this, and then remember what we want to do is we want to take the square of the derivative and add 1 to that. I made a mistake here. Let's go back and fix it. This should be a minus sign here. And so there's a minus sign here and here, which makes both this term and this term negative, and so these are actually both negative 1/4. So negative, negative. So continuing, we've got this is x to the 6th minus 1/2 plus x to the minus 16 over 6, and then we're adding 1 to that. And when we add 1 to that, we get this, x to the 6th, the minus 1/2 changes to a plus 1/2, and then the last term, of course, stays the same, plus x to the minus 6th over 16. So the significance of this is that we started off when we squared f prime of x as having a minus sign between as the middle term, and now we have a plus sign. So let's do a little bit of algebra here to illustrate what's going on. So you remember this from back in your earlier algebra. The perfect square is a squared plus 2ab plus b squared. But if there is a minus sign between a and b, it becomes a squared minus 2ab plus b squared. And so what we actually have here, when we add the 1, we change what that perfect square trinomial we have under the radical from this form to this form. So this expression right here where we left off is actually one that can be factored like this, right? X cubed plus x to the minus 3 over 4 quantity squared square root, right? And if we go back, we see where we were before is that we had x cubed minus x to minus 3 over 4 at that point. So that's actually a very good thing, because now what we have an expression under the square root sign that we can take out of the square root sign, and so we get that our arc length is just the integral 1 to 2. The square root of something squared is just that something, so it's x cubed plus x to the minus 3 over 4 dx. We can integrate both those terms. When we do that, the x cubed goes to x to the 4th over 4, and the other term, we're adding 1 to the power and dividing by that power, so it becomes the x to the minus 3 becomes x to the minus 2, and we're dividing by minus 2, so it becomes minus 8 in the denominator, and we are evaluating that between 1 and 2. Again, we're going to appeal to a software solution here. Oh, actually, no, we can do this. We can actually do all of these calculations here, right? We've got 16 over 4 minus 1, x to the minus 2 is squared in the bottom, so it's 8 times 4, and then when we plug in 1, we get what? 1 to the 4th over 4 minus 1/8, and that actually gives us 123 over 32, which is approximately 3.84. So this is a special example here where the function is such that when we take its derivative, it's an odd-looking function and an odd-looking derivative, but when we square it, we get this. And when we add 1, that minus 1/2 middle term turns to a plus 1/2 middle term, which allows us to change it from this factorization to this factorization. Or in other words, it's a plus b squared, so the radical, so the expression comes out of the radical, and we can actually do the integration. So not very many problems of arc length are going to be of this type. This is just a special kind of problem that does come out. The more typical type of problem would be even with simple functions where we can't do the integration and we have to do it using some numerical method. So this gives us goes through examples 1 and 2 in this section, and this is going to be the conclusion of this video. The first half of this section, 6.4, the other half is on surface area, and we're going to do that in the next video.